Okay, we're going to continue our lecture on the interaction of radiation with the atomic and molecular system. Last lecture we saw the principles of the electromagnetic waves, just to like a revision to really understand what's coming later. And we showed to you that when we talk about electromagnetic wave, we have to think, of course, in photons, as we discussed before, but we have to think now in this approach that we're going to use in electrical and magnetic fields oscillating in time and space. And this is a wave picture, and we even showed to you that in this picture we can calculate the density of energy that's contained on the radiation, and that's the energy that will be somehow transferred to the atomical system. And we realized that a better way to express the electrical and magnetic field is using a third vector, which is called the vector potential. And the vector potential is a quantity that allow you to get the electrical field and the magnetic field of the radiation. So with a single quantity, which is the vector potential, which is the capital A, we can obtain the electromagnetic radiation. Therefore, we use, and this is in the basics of the electromagnetism, in the Maxwell equations, right? And we show that the energy density in the electromagnetic radiation actually is the amplitude square of the vector potential. And since now going back to the picture of photons, you know, an integer number of photons in the radiation field, we showed to you that actually the density, which is an integer number of photon energy divided by a volume control, is given by the number of photons contained in the system. Is actually the amplitude of the wave vector. Of course, we are dealing with some specific frequency, but normally the radiation can be composed of many of those vectors, with a spectrum of those vectors. And A square, the amplitude square, is therefore the number is related to the number of photons in that control volume. In that sense, we can calculate what we call the intensity of the radiation, which is the flux, which is the flux of energy, or energy per time per unit of area flowing in the system. And that's typical what we use in laboratory or any specification. And that is actually directly related to the number of photons, because the density times the velocity, the density of energy times the velocity of the radiation, which is the propagation velocity, give us the intensity, the flux of energy. And speaking about intensity, we are speaking about number of photons in the field, right? And of course we have all those quantities that compose this intensity. Well, so with those concepts, we can go on and tell you a little more about what's going on when the electromagnetic field interact with the radiation. And the first question is, what does the electromagnetic field cause during interaction with atomic or molecular orbitals? Right, so then here you have to use your intuition. We're gonna abuse a little bit about the classical intuition, but we're gonna go to the quantum. So imagine you have a orbital, like a s orbital of the atom. So we have a s orbital. And this s orbital, as we saw when we solve the atomic system, is like a spherical distribution, right? It has some radial profile, but it's like spherical. Now imagine this electrical field coming in one direction, oscillating. What is going to happen is that this cloud is going to start to oscillate. because the electrical part of the electromagnetic field makes a force on this. And when the field is up, the cloud is down because the charge is negative, right? We know that the charge is negative. So this is the place that actually is occupied by the electron. It's negative. Probabilistically speaking, right? That's the distribution of the charge of the electron, because that's the picture of the wave function square, which is the density of this particle in the space. So when the electrical field acts, it can bring this cloud up and down, and it may be that due to this interaction, the cloud gets closer to be one of those p orbitals. Because we have to understand that the electron in the atom, it has to stay in either of the many possible states. And the many possible states, they have a different spatial distribution. So the electromagnetic field will act on this and maybe will produce a new distribution. So we'll make sure that the atom can go from here to a new state. And that's what we call electronic transition, caused by the electromagnetic field. So the electronic transition caused by the electromagnetic field is this effect of the action of the components of the electrical and magnetic field on the atom, promoting a change in the wave function, promoting a change that will make it stay in the next one. Because you see, this and this, at the moment, they are both stable states. We did not introduce yet the so-called spontaneous emission, which is the effect of the vacuum, or the fact that we are in a space to make this orbital to decay to this one and send light out. We didn't see that. For us, at the moment, all the orbitals are equally stable. Therefore, if you have a physical entity able to take the spatial distribution in one state and put in the next one, the atom will stay there. So that's the essence of the electronic transition. Is the action. I took a radical situation because you can see very well that when the electrical field acts on this, we'll try to bring up and down, give you some view that because of this action, the distribution will look like this, which is the next orbital. So the energy, the action of the electromagnetic field on the cloud, transform it in the next one, which is very close to the state. And of course, sometimes this is a weak field. It has a tiny little possibility, only deforms a little bit this cloud. And deforming this cloud, it has a little chance of having this. Deforming a lot this cloud has a big chance to make this transition. So the chance of transition depends on how strong is this action. That is an important view of the problem, right? And that's the way you have to think about. And of course, in this process, many things can happen. We have always to remember that the atom has a spin, the electron has a spin, and in this thing, the magnetic field may act on it. So there are also other possibilities during the action of the magnetic field on this. But in a first approach to understand empirically what's going on, or to develop our vision of it, or intuition, you have to think in the interaction of the electromagnetic field with the atomic levels in this way. So this is a very powerful thing, because the light going to the atomic system makes to change the orbitals and can cause transition. And the opposite, that's what's interesting, the opposite is also true. We know that this is more energetic than this. So for going from here to here, we consume energy from the electromagnetic field. Now, the opposite could happen, right? You could be here, your system could start in this configuration, and then you introduce the electromagnetic field, and again, will happen the same. It may be this will bring back this cloud by action of the electrical field that looks very much like this. And looking very much like this, you make the opposite transition, but this is less energetic. So in this case, the electromagnetic field at the end got a surplus of energy from the atomic system. So if we, in this case, which is a peculiar state, we have also changing spin and everything that we're gonna review and do to you. First the basis, then we come to applications. The change of state is actually related to this action of the electromagnetic field on the charge distribution. You know, because the atom is made of charge and the electromagnetic field is made of electricity and magnetism, they have a strong interaction, right? They have a strong interaction. Now, it's you know, to go from here to here, you need, it's more efficient when you have the right energy of the field to be given. And at the bottom line, we are using a kind of a classical picture for the field. But actually, when this happens, there is a transmission of one photon of energy. So it will be easier when the photon has energy that somehow matches well with the energy transition of this. So what Bohr was saying from the jumps between the trajectories in his atoms, actually he means this. That's what he meant. The energy of the photon has to match the energy the atomic system needs for making a jump, going from one stage to the other state. This is an important part, because if you have this in mind, even though you don't follow all the steps of calculation, you know exactly what's going on because you have a feeling for, right? Well, sometimes it's not exactly this. Sometimes you have a complicated molecule and the electron that are making the chemical bond will suffer some modification, and then you have this interaction. Or sometimes you put a photon and get another one, but at the end of the day, you provoke the two nucleus to vibrate, and that's a vibrational excitation. And of course, the field has to have special characteristics to promote this. This is a simple picture. In this picture, you know, the oscillation of the electromagnetic field easily can be seen by anybody that will deform this charge configuration and promote the transition from one orbital to the other. But in some other cases, this is very subtle. I mean, you have to see a little deep. How is the field configuration? How is this? Sometimes you need the field to be rotating because you have to introduce, besides the change, you have to introduce angular momentum and everything. And that's a more fine view of this effect. But the overall effect is what I just told you. Right? So, we have now to make our view of the interaction more accurate, so we more precise in a way that we can understand this using the basics of the quantum mechanics, because the quantum mechanics has to be, it's true, right? We believe it is, so it has to be able to show that when I put electromagnetic wave in a system like this, the result is something like that. We have to be able to understand that and to demonstrate. And that's why we're going to start to elaborate now. We're going to start to elaborate using the wave equation. That's the best thing we have. We're going to start to elaborate how can an electromagnetic field causes such a tremendous variation, causes the atom to go from one configuration to the other. But as I said, and I insist, you see, the system cannot be in anything intermediate. When you do a measurement, you either here or there, because that are the two things allowed. Those are the two waves that the electron can be, predicted by the wave equation. So the electromagnetic field can only go from here to there, right? Sometimes it's a tiny little, and then the probability for causing this is lower. Sometimes it's big. And as we're going to see later, this may be oscillating between one and the other in very, very interesting phenomenon. Okay, so we have now to put the mathematics in the wave equation to be able to predict that in the presence of the electromagnetic field, those transitions will take place, and we want to evaluate with what's the frequency, what's the rate. If I turn on a light and shine into atoms, what is the chance per unit of time of transitions? How many times the atom will go from here to here or from here to here? How many times? And many people was worried about this, and even Einstein made a very nice detailed balance of energy kind of calculation to show how things goes, and the probability to go from here to here is the same of coming from there to here, right? So these two ways, that way and this way, are equally probable, independent where you start. Very good. Now we have to start the mathematics to put this in the equation and make sure we can somehow build up those probabilities and those have expression for the rate of going from one place to the other, the rate of transition we call. Well, to do that, we always work with energy. Sometimes we call Hamiltonian, right? Which is the energy put in those specific coordinates. And when you have an atom or any charge, because here the essential part is electromagnetic field, now we'll add to the Coulomb field. The Coulomb field of the nucleus is keeping the electron around. And now I have to add the action of the electromagnetic field on the electron. Well, the electromagnetism, together with the classical mechanics, they did a very good job on this description. And they were able to prove, we're not going to do here, but you can find, if you are very interested in this, you can find in any book of electromagnetism or even in classical mechanics, you can find that. And what's happened is that under the action of the electromagnetic field, which is now represented by the potential, the vector potential A, the momentum of the electron takes another shape, takes another form. Instead of using the conventional P, which we are used to, it takes the shape of P plus E over Ca. When you replace the momentum of the electron by P plus E over Ca, you are dealing now with an electron in the electromagnetic field. So all the consequences of the electromagnetic field must be in this transformation. This is the real momentum, or the momentum that obeys the basic laws of the classical mechanics, in fact. It's this momentum, not this momentum. So, even though we are not proving this because, lack of time, this is something nice to know and to take a look in the books around, or I'm sure you can go to the internet today and find the deduction of this. So what they call the canonical momentum of the electron or any charge in the presence of the electromagnetic field, represented by the vector potential A, can be fully done if you make this transformation. So you make this, that's the real momentum you have to use now. when I say the real momentum is this, is because the kinetic energy, or the energy part, will now be changed. All the action of the electrical and magnetic field on the energy of this system will be changed by making this replacement, by adding this term. So this is like an extra momentum introduced by the presence of the electromagnetic field acting on the electron, on the charge. So the energy of the system, as we know, is P squared divided by 2m minus E squared divided by R, which is the kinetic part and the Coulomb part. That's the energy of the electron when it is in the neighborhood of the nucleus. Now, if it, together with being in the neighborhood of the nucleus, you also have an electromagnetic field represented by this vector potential, we have to replace the P by this. And I hope you trust me that this is this is well known, and we can prove that and everything. So the new energy of the system, which is always our starting point, is given by not that, but this. You have really a motion part here, which is the P, but you have also an extra term that's introduced by the electromagnetic field. When you do that, that automatically adds a term on the wave equation that represents the participation of the electromagnetic field on this, right? Because remember, we start with this, and instead of the momentum, we show that because we are looking for the wave, this will be a mathematical operation, will be the second derivative, the momentum square, with respect to the space. Now, when we put that way, we see clear that we have this term square that will stay there. There is a product between this and this, because this is square, and then there is this term square. This term square, they all important here. They all important here. And at the moment, we're going to keep it only to the first momentum, because we're going to say that the term that goes with the a square itself, we're going to leave behind at the moment. And then when we speak about more than one photon transition, we're going to return to it, right? We're going to return to it when we explain to you some applications of all of this. So this is the new energy that we have to use. So it's very simple. We just go and reconstruct the wave equation, replacing the momentum by this term. And then there will be some extra energy terms in the wave equation. Because basically what we do is convert, this is the energy, and we say that this is a mathematical operation now to determine the wave function. That was, you have to recall now how we constructed the wave equation. We construct the wave equation, start with energy. That should be the truth. And then we went and say, okay, but the momentum is an operation on the wave function, right? And then we constructed this, and we construct a very nice master equation. And because we were dealing with time-independent potential, we just say that the time variation of the energy was the energy, right? But this was the starting point. Now we're going to have to come here again and remember that energy for us is IH bar variation with time of the wave function instead of the energy. And then here is the momentum. We know that if we want to determine, if you are based in wave function, this is the derivative, right, of the wave function, and twice it comes to be the Laplacian. We did all that when we build up the master equation. But this part here, now we have to keep it because things will vary in time, so we have to keep that. we know that we start with a system that was stationary, that was with possible states, possible waves in the configuration of that potential. And those are the states we have there. But now we are introducing something that varies in time. And this variation in time has to be well taken care. Therefore, the energy here, because now we'll be able to change in the system from one to the other jumps, we needed to keep it explicitly, the time variation. Okay? Okay, very good. Now we're going to base it on this, base it in what I just said to you. We're going to construct or reconstruct the wave function for this case. Remembering that this is adding little energy. It's not the major part. This is adding very little energy to the problem. And you have to keep it what I said, the intuition, that actually this time variation of the interaction will promote the system to migrate between the states. This will promote the system to migrate between the states, right? This is what the action of this time field, which is the electromagnetic radiation, will do to us, or will do to the atomic system. Okay, very good. Let's then consider again the Schrödinger equation, but now including that term. Instead of the momentum, we have the momentum plus E over C, E being the charge of the electron, times the vector potential that represents the electromagnetic field. When we do that, we just needed to come and take the square here, right? But with the care that this is now the gradient. This is a mathematical operation on the wave function. So we cannot really commute everything. So we have to keep the order there. And when we do that, we regain the original terms that we had. So we had the two original terms to determine the wave function, right? Plus a term. I'm kept only the term, not the linear term with A. So this is about, because I neglect at this moment, for this part, the second order in A, which means the A squared term that will appear here. That is a square term, of course that is a square of A term. But I will return to it later, because that represents what we call nonlinear interaction of the radiation with the atomic system, which is a very important thing, but at the moment you have to learn the linear. This is the basics, right? So fundamentals of the quantum science applied to this. And believe me, the interaction of radiation with the atom and molecules is one of the most important bases of the biomedical type of application, because we use everywhere. This is used for analytical determination, for therapeutic applications, for many things. So we gotta learn that. This first part here, as you know, this first term here, that's the original part. So this part is the original atom. These, if you forget this, if we zero out the electromagnetic field, means A0, there is no electromagnetic field there. We recover the atom with the states that we already discussed. Now, this next term, that is the addition. This term is actually the addition of the interaction. So that is the interaction with the field. And this is the one that will cause a lot of things in here, right? And I didn't say that this is equal to the energy, even though it is, but it's now represented by the time variation of the wave function, because We have to keep that because this has time variation on it. It's not like we say that, oh, now the electron interaction with the external world has no time independence. That's what we did before, and that's is a value of the energy, and that's it. Now, no. Now this is time independent, so we have to keep the time independence here. What's going to happen in this situation? Well, I told you already, and we're going to show you mathematically that what's happened is that the time variation of this interaction makes the system to occupy different states and oscillate between them. And of course, that will depend on the frequency, because here on A, there is the omega, which is the frequency of oscillation of the electromagnetic field. So omega is here. There is an omega here that determines the frequency, the time oscillation frequency of the electromagnetic field. So in principle, that's why it's going to happen. The system can start in one state and go to many other. Because of this, and because of if I don't have this interaction, the solution of this problem we already saw is this guy here. The solution is a spatial part and the time part, and the time part is the oscillation that's depending on the energy. We told you this. The energy of the states, right, determine the time oscillation of the wave function. And the spatial part depends on the potential that holds. But because now we introduce this extra interaction, which is time dependent, I don't know exactly where the atom is going to be. So the best is the solution is a composition of all the states. This is deeper than what I'm making. Actually, the solutions of an equation like this produce a set of functions that is a complete set. Any solution of any equation can be placed as combination of those solutions, right? This is what we call a complete set of functions. But here, because we already made the interpretation, it's easier to understand that what this interaction is going to do, because it's time oscillatory. Sometimes exists, sometimes doesn't, and then reverse and comes back. Will transfer energy to the system to be in any of the states of this equation, right? As I told you before. So the solution actually is a composition of all the states of this system without the presence of the radiation. But with an important differentiation, the composition is time dependent. So this is time dependent. The coefficients of this sum of all possible states of this Hamiltonian is time dependent. That means the electromagnetic field are able to, because of this equation that's time independent, and this is time variation, and this present times variation, will change this coefficient in many ways. So as the time progresses, it is possible to be in different of the states. And this square is actually the probability, for the system to be in a specific K state. And what is the K? The K is the solution of the original equation without the electromagnetic field, which is here. right? Those are the atomic orbitals. We're dealing with the atom. That's the most interesting things here, but it could be anything. So the solution of this generated this set of orbitals, as we saw. And those orbitals, they now compose the overall solution for the problem. Total psi is a sum of the individual psis that are solutions of the atom isolated. So it's clear that what's happened is that the electromagnetic field is promoting superposition or promoting chance for the system to be everywhere, starting everywhere. Normally, we like to start in the what we call fundamental state, which is the state of lower energy. But then the system can migrate through this interaction to the other states. And of course, because this has to be, if I multiply this by its complex conjugated, which is the probability density, and integrate has to be 1, the sum of all those guys will be 1. Remember that the orbitals are orthogonal each other, so when I try to integrate one in the other, they give you 0, right? I told you this. I already mentioned this, but I will make sure to complement even more this concept. So this is the probability that the system, I have this, I have my atom, I turn on the electromagnetic field, oscillating, the system can be in any state. And the probability to be in any of those states is the ck square. Or the probability to be in any of the k state is the modulus of the ck square. K here is a sub-index. So this coefficient is, now we know those states. We already solved the atom. What we need to determine is what are the values of ck. That is what we do not know yet. And we must somehow determine to be able to understand what are the mechanisms, what's going on in the system. Okay, well, we are progressing very well, very good. But we cannot go very fast, otherwise we're not going to understand. Now we're going to start some calculation. Really, because I have to determine the ck's. And to determine the ck's, I have to rely in a few properties of the function. And those properties are properties that are fundamental for the quantum mechanics. So those properties are very important, and actually those properties is common for any quantum system, and we need to know, even though I told you already, and I keep giving in small doses those concepts for you, so that start to aggregate on your knowledge about the quantum effects. But we have to understand what means a solution of a quantum problem, right? In terms of what properties those functions they have. So I can deal with this problem now easier. So this is what we call a complete set of functions. Complete set of functions is when we solve the problem and we get these functions that represent the atom, that's the whole universe for the atom. That's everything the atom can be by itself. It cannot be anything out of that complete set. It can be any of those states. The orbitals that we determine, they constitute a complete set. The atom has to be in one of them. It cannot be in two. It cannot be in something that's in the middle, right? Sometimes we combine atoms and then we get orbital with different shapes and different possibilities which correspond to different wave functions. But normally, the set of functions that we determine for the atom is everything the atom can be. It cannot be in between. Of course, the external things can change a little bit, this whole thing. And then that's why we call a complete set. It's the whole universe for the quantum system. any solution for the system has to be expressed in terms of a combination of those states. In fact, the quantum mechanics is so robust that when I solve a quantum system and I get a collection of solutions, I can represent any other system in terms of that, because that's a complete set. Any function in the world could be represented in terms of combination of those. That's what we call a linear independent composition of functions. Like as we learn with the vectors, linear independent vectors, and any vector in the world in that space can be represented by combination, linear combination of those. The bases of the vectors are this called linear independent bases. And here we have a set of functions that makes a linear independent collection of functions. Therefore, any other function could in principle, in this space, be represented, be expressed in terms of combination of those functions. It's very similar with the vector. And of course, we normally have in 3D, you have three vectors, but in the quantum system, we may have infinite wave functions. So the set may be infinite. Or sometimes it's finite, as we're going to learn later on in a two-level system and so on. So this is an interesting concept that we have to use. Another concept, as in the vectors, those functions, they are linear independent, so they are orthogonal, which means when I make a product of two of those base functions, they give zero. That will be the starting point of our new lectures, and that will be the last lecture where I'm going to conclude the interaction of the atom with the radiation in this base. Then I'm going to do the two-level approach for us to progress in this nice course of fundamentals of application of quantum science in bioengineering. Okay, so see you in the next lecture.